Morning, and thank you, Tim, and the Skagen team for the pleasure of joining you in a southern latitude, at least south of where I grew up in Canada. It's a pleasure to be where the sun sets so early. Uh, I'm heading to Miami this afternoon. As Siri said, I'm going to talk about not investing per se, but a technological macro. I am involved in. I am interested in investments, but having been trained and spent my early career as a physicist, I tend to focus throughout my life, whether it's in the public policy or in the investment world, on underlying facts and phenomenologies, if you like. So the world is at, people say this a lot, at a pivot. It feels like we're at a pivot point. The pivot in energy sense is in the direction of what everybody is talking about, which is the energy transition. And the key issue with the energy transition rhetoric and policies is not one about aspirations, which I'm not going to talk about, and not one about structural possibilities, which are non-trivial, but rather it's about minerals and mining, as Siri pointed out. So my focus is almost entirely on that. And in a sense, this is not naked adulation for Norway. It's, in a sense, the policies of the world are focused on trying to become Norwegian. I have stolen the famous Kennedy line, Ich bin ein Berliner, to translate it, I think, correctly into, I want to be a Norwegian. I mean, Norway last year, as I'm sure you all know, had the record in the world. 80% of all new cars were electric that were purchased here. Norway gets 90% of its electricity from renewables. It gets half of its primary energy from renewables. This is, in essence, the goal of the entire energy transition world. That's, in a nutshell, where the world thinks it must go or where it thinks it can go. I mean, Norway has some advantages, maybe perhaps obviously. It's wealthy. I mean, it's 700% wealthier than the world average. It's wealthier than America by a significant margin, even in economically challenging times. I think it's about 30 to 40% wealthier per capita than America. Norway also enjoys the benefit of exporting, in dollar terms, something on the order of $25,000 per capita of oil and gas sales to the world. This, again, in production terms, is about 400% greater per capita than U.S. oil and gas production. And the U.S. remains the world's biggest absolute producer of oil and gas. So those are advantages. And the other advantage I would point out, which is in the underlying physics of energy, is of course the renewables that Norway likes to use and is dominantly using have a particular advantage. The machinery, hydro dams, last about 4 times longer than the machinery of preference in the energy transition, windmills and solar arrays, and they produce roughly 4 times more energy per dollar of capital invested. So that 16-fold energy economics advantage is a modest leg up over the rest of the world's aspirations. But that said, this is the vision. And to point to where I'm going to go, the vision incorporates a fact built into the nature of the world we live in at the moment, which is that every Norwegian that buys an electric vehicle has essentially purchased 20 to 30 barrels of oil equivalent of energy being consumed somewhere else, and fully half of that energy content, in fact, is oil, and the rest is almost entirely coal and natural gas. So the single EV that is purchased in Norway, when it goes on the roads before it's seen its first electron move into its batteries, has already consumed at least 25 barrels of oil equivalent of energy in hydrocarbons. The question about whether the world will become Norway or not is one of velocity and materials. And by velocity, I mean the world today is just a statistical fact, and we have to put this out since you probably all know this, but one has to have this in one's head, that the world today gets about 3% of its total energy supply from wind and solar, the preferred sources of energy in the energy transition. Essentially, all the IEA and IRENA plans, the World Bank, all the energy transition aspirations pivot around wind, solar, and batteries. 70% of the net new energy supply in the forecasts in the next 20 years are to come from wind and solar, mediated by batteries, whether in cars or on grids and in buildings. So 3%, well, that's not nothing in a world as big as it is, but just, again, it's a sense of whether or not we have made a transition as opposed to having an aspiration for a transition. 3% is obviously not a transition. In fact, that's 1/3 as much energy as the world gets from burning wood. The oldest source of energy other than muscle in the history of the human race still provides 350% more energy to the world than all the world's wind turbines and solar arrays combined. This would suggest that transitions are slow and difficult and expensive. The world has spent something on the order of $5 trillion in the last 15 years in direct spending, and probably that much again in indirect spending, to achieve a change that is not, in fact, in semantic terms, a transition. So the transition is really about the future. And the scale to go from 3%, let's say, to 10% of world's energy from wind, solar, and batteries is also not a transition, but it would be quite a remarkable accomplishment. If you think about the state of the spending and the state of where the world is today, a 300% increase in a very short time period in capital spending and physical infrastructure is quite remarkable. And there's no shortage of money that's being allocated to making this transition happen at all, if not try to accelerate it. This total capital spending, this is IEA data, in the green transition is on a tear, to say the least. I mean, we're spending now something in the order of $800 billion a year direct money, and I dare say that the real numbers are higher because mandates have a real cost to the economy. Mandates, that is, all over the Western world, governments are requiring utilities and energy companies to make transitions that don't show up in direct spending, but they show up in the real costs to the economy. So there's no shortage of spending. And I show you the conclusion from a very recent Electric Power Research Institute study, which is a nonprofit research group in the United States for the electric industry, that looked at the structural issues with respect to the transition. Not the cost issues, but the structural issues, and reached the conclusion that, you can read the conclusion, that it doesn't look like it's structurally possible to make the transition in the way imagined. The typical response to that is we should spend more money and try harder, which is not an unreasonable response in the face of structural concerns. I would hazard the opinion that spending more money won't cause the structural issues to go away, but that's not what I want to talk about. What I want to talk about is the fact that what's interesting to me is that one particular study, typical of most, completely glosses over the underlying question of where do the materials come from. So let me turn specifically to this material and mineral issue for a very simple reason, sort of locked into the reality of the world we live in. There is no shortage of energy. Energy is not in short supply in the physics of the universe we live in. Energy is, in fact, an infinite supply. Energy, for all functional purposes, all forms of energy, are functionally an infinite supply. The challenge for humanity has always been in figuring out how the systems work in nature, designing machines that can extract nature's natural energy sources and convert it into forms that are useful for humans at a price we can afford. And price is principally economic, but price also includes social, environmental, and geopolitical features. These are all costs, but they all distill ultimately to money, and they all require machines. One has to build machines. All machines wear out. It's the nature of the universe we're in, probably the most enduring law of physics, entropy. We age, things wear out. This is true of all machines, of batteries, of solar arrays, combustion turbines, and cars. So the wearing out process means that you're always in this sort of Sisyphean battle of building new machines, finding new materials. The IEA deserves credit at the sort of structural staff level for doing some of the best, frankly, and most comprehensive work looking at the structural underlying engineering economic realities of any of the organizations that talk a lot about the energy transition. It may not be the top line issue that the IEA talks about when Fatih Birol speaks to the world. He rarely talks about these issues. He does sometimes. But this data that I'm showing you in this graph comes from IEA report. This is the underlying single fact that's built into the energy physics of the machines that are the principal vector in the energy transition. Again, wind, solar, batteries, and electric cars. The underlying fact that's important is the quantity of minerals needed per unit of power to build the machines. And I've taken the whole basket of minerals, which is not just copper, and I've made copper and everything else as opposed to copper, molybdenum, lithium, neodymium, manganese. There's a suite of minerals, aluminum, essentially a basket of 24 minerals that are essential to the building and construction of batteries and energy transition machines. But if you just divide it into two buckets, copper and everything else, you get this picture. To build a machine to replace combustion turbines, what this shows you is that you need between 1,000 and 2,000% more minerals to deliver the same unit of power. And you need somewhere in the order of 400% more minerals and metals to deliver the same vehicle. So an electric vehicle requires 400% more metals and minerals to build it compared to a conventional car. But this is, in energy terms, this is understating what's actually going on because, as I said at the outset, the advantage hydrodams have over windmills and solar arrays is that they operate very differently. Obviously, hydrodams, especially in Norway, produce energy more than 90% of the time. Windmills and solar arrays self-evidently do not. So if you adjust this data for energy delivered as opposed to power, the actual requirement to deliver the same unit of energy to society is a 2,000 to 7,000% increase in the metals required to deliver the same mile of driving, the same hour of heat, the same hour of illumination, the same hour of compute time. So this quantity of minerals required to deliver the same energy service to society has a consequence. I mean, if you go back upstream, and again, IEA data, they aren't alone in doing this. The Finnish Geological Survey has done similar work. Many other serious organizations and researchers have looked at the implications of the massive increase in metals needed per machine and look upstream to how much more mining does that mean. And well, it means, and this is a down selection into the a suite of 5 minerals that are the obvious ones, right? Cobalt is still a relevant metal despite the attempt to minimize cobalt use. Cobalt is pretty much in every single electronic device battery because it adds a feature of energy density that's critical. It's still in most electric car batteries, but there are options to cobalt, typically nickel, and there are some other options. But before we get to the options, the key fact here that is central to the question of how fast and how effective and how expensive again in every term, economic, geopolitical, social, environmental, how expensive an energy transition will be with machines of the kind that are now being built is anchored entirely in this one slide, the magnitude of increase in the amount of demand for metals and minerals in the world. Put this in percentage terms because when we talk about growth, if you're in a business, you talk about increasing supply or demand, depending on which side of the equation you're on, in the heavy industries by numbers like 5 or 10%. A movement in oil markets of 5 percentage points is massive. I mean, 5% loss of demand or supply. If it's a 5% loss of supply, prices take off. A 5% increase in supply with demand not following it is a huge collapse in price. So 5 and 10 percentage points changes are huge in commodity markets. This is a change in demand from 700% to on the order of 4,000% in total supply of these metals. And this is the increase in demand and the increase in, therefore, supply that will be required in the coming 2 decades. Not to put too fine or hyperbolic a point on this, this would, if it were to be achievable, is the largest single increase in demand or supply of metals in all of human history. It's never happened. So in the title of my presentation, when I put the question and used the provocative word delusion, by delusion I don't mean people are delusional about their aspirations. I think they're suffering some modest delusion about what the possibilities are in the mining sector. I mean, the whole thing distills to mining. Is it possible, can the world increase the production of these kinds of metals, not by 10 or 20%, not by 50%, not by 200%, but from 700 to 7,000%, and in time frames that are meaningful, which is in the next decade or two. If you think of this in the macro tonnage terms as opposed to in terms of kilowatt hours or machines, and look at it from the context of the total tonnage of all materials that humanity extracts, moves, and processes to keep civilization running. This is an OECD data series. It tells you something that's important, again, from an economic and environmental perspective. The world, all kinds of materials, biomass, food, fuel, construction materials, has to extract, move, and process about 100 gigatons of materials a year. This is a remarkable increase over the last 50 years, from 25 gigatons for the planet. This trend is not going down. This trend line has implications, again, across all domains of economics and environment, geopolitics. But the thing I want to point you to is the energy part, which is, as you can see, the oil, gas, and coal, and this is measured in tons terms. What we're proposing to do with the energy transition is to shift the majority of the world's energy supply from liquids and gases to solids. So measured in tons terms, what that means is that you will increase the wedge that's in gray by tenfold. Or put differently, the energy system in the future as imagined in the transition will require the extraction and movement of quantity of materials equal to or greater than the quantities of materials that humanity extracts, moves, and grows for all other purposes combined. I don't think that's going to happen. I mean, this is not a statement of politics or a statement of aspiration or an objection to motivations. It's just not going to happen. The world's not capable of doing that with the technologies that exist today. These are astonishing numbers. We also know a lot about the minerals and metals world. I think the Skagen team is particularly expert at this, I'm told. I've had some very interesting conversations about travels into the fragile political and physical ecosystems where we do all this mining, which I'll get to. We know a lot about mining. We've been mining for a long time. Mining is the oldest industry, full stop. Mining, in fact, copper is the oldest mined metal, and it predates written history. We know a lot about mining. What we do know is the world is not now mining enough materials, nor is it planning to mine enough materials. I'll pick just copper here, but this, and you all probably have seen various photographs of the world's biggest copper mine in Chile. It's a very, very large mine. You can barely see the town that's at the edge of the open pit in Chile. So the world produces enough metals right now to supply the transition machines for a very simple reason. They constitute about 3% of the world's energy. If we imagine tripling the share of the world's energy coming from wind, solar, and batteries, we will necessarily have to at least triple the quantity of metals those machines require to be built. We know for a fact, this graph shows you the red line, which is the demand that the energy transition will put on copper. We know that the supply lines, which are the dark blue, existing mines, and the light blue lines, which are all existing mines, plus all announced plans for expansion, whether underway or proposed. Put in simple or simplistic terms, the world will be short copper in a year or two. That there'll be physically less copper available in the world than the demands of the energy transition will place on it. What happens in a world like that? Well, I like S&P did a big copper study. If you haven't seen it, I commend it. I think it's available for free from IHS S&P. They ask it in a very diplomatic, gentle way, will the shortage of copper short-circuit the energy transition? The question answers itself. Copper is not, it turns out it's one of the metals that does not have a substitute. It's not replaceable. The only place copper for electrical purposes has a substitute is aluminum for high voltage, long distance transmission lines. It does not for electric vehicles. So if you look across all the metal spaces, you find similar graphs. I'm not going to go through them all, but you can pick every metal. You can pick lithium and cobalt. You can pick nickel, aluminum. There's a shortage of all the metals in the coming years. The IEA has pointed out the world will need hundreds of new mines to meet the materials demands of the energy transition. And what they've also pointed out, something that's beyond obvious to anybody that's worked in mining. Early in my career, in my impetuous youth, I worked for a mining company. I never thought I'd come back to talking about mining again. It was a gold, uranium, and silver miner in the Northwest Territories of Canada on the Arctic Circle. It's maybe the only one in this room that's been to the bottom of a 7,000-foot vertical hard rock shaft. It's very dark and very hot at the bottom, but it was very interesting. I like mining. I like miners. I think we'll do a lot more mining. And the problem is the average is about 16 years to find and open a new mine globally. Or if you think about this in very simple terms, that means that if we tomorrow started investing the necessary amount of capital and exploration efforts, it'll be 16 years before the first mines that we need will be open. You can do your arithmetic on this. This is a long way after the aspirations have kicked in to build the quantities of batteries, windmills, and solar arrays that the world imagines outside of Norway. And we also know a lot about how much money the world's mining industry is spending here. This is Wood Mackenzie's graph. They did a very nice job last year mapping out the historic capital spending globally in top metal mines and the forecast. The hashed lines are the levels of investment that will be required in the next few years. The dark colors are the levels of actual investment from the global mining industry. We can distill this not in dollars terms and billions of US dollar terms, but just in relative terms. The world is not investing 90% of what's required or 50% of what's required. By world, I mean the world's miners. They're not even investing 10% of what's required in global mining expansion to meet the aspirations to build the quantities of machines to have, again, the rest of the world follow Norway. We also know something about the geopolitics and the social features, if you like, of mining. The mining is elsewhere. It's not largely in Europe. The expansions are not in North America largely. They're in sub-Saharan Africa and they're in South America and the Asian nations. I happen to like trade. I mean, this may be an artifact of being from a country with, like Norway, small numbers of people and large quantities of resources. So I'm pro-trade. I'm a trade bull. I think the world should do these things. But I think the world should not be naive about both the social and environmental problems that occur as we expand mining in these parts of the world, nor the political and economic challenges and the geopolitics. China is not the world's biggest miner. They are the biggest refiner. And when you measure it in energy minerals terms, again, this is IEA data, China's share of refining, when you must refine copper, you must refine lithium. You can't use lithium in its elemental form in lithium batteries, nor any of the metals and minerals in elemental form. They all require the very inconvenient, very expensive, and very environmentally challenged process of refining. China has chosen to become the world's energy minerals refiner. This was not a secret policy. They announced it 20 years ago. They announced it in their 10-year plan 10 years ago. And today, China enjoys a market share in global energy minerals refining that is more than double OPEC's market share in oil markets. That was a smart strategy, I would offer, but also has implications geopolitically and economically that it would be, to put it diplomatically, profoundly naive to think it has no implications for the state of the world as we go forward. It also has implications economically at the macroeconomic level. This is an analysis that I'll show you one graph of many from an International Monetary Fund paper that was done about a year ago. The economists there did something that I'm shocked that more analysts have not done. The economists at US Geological Survey have done a similar analysis. And it's a very simple question that they asked. As economists, if the world chases if there's more demand for a product than the world can respond in supply, what will happen is inflation. This is not complicated. That's the textbook definition of inflation. The question you would ask is how much inflation would we get? What's the range of inflationary pressure on metals as the world chases the energy transition, but the world's miners aren't able to supply the quantities of metals? And they answered the question with the typical, you can see the pink zone, a graph depending on the assumptions you make. The underlying fact is one, prices don't go down. They just don't go down. If you have 16 years to add supply, on average a decade at best, and you increase demand immediately, which we are now doing with policies everywhere in the world, you should expect prices to not only go up, but to perhaps go up a lot. In fact, their principal conclusion, which I replicate here, is an important one to have in mind. They've looked at a century of trailing data on supply-demand metrics for metals, and they point out that the energy transition plans will put pressure on metals that will cause all metals to reach historic price levels for an unprecedented length of time. They think for about a decade. So metals then go from being just volatile and short time frames with being volatile over a much higher price base. This should have an effect. It will have an inflationary effect. I mean, first of all, at this current level of abstraction, the cost of metals in the world's economy is in the noise. A few percent of the global GDP is consumed by the prices of metals. But if you cause metal prices to go up 200 to 300%, or 400%, or in lithium's case, 1,000%, you'll see it have a top-line effect in global inflation. So while I think inflation moderates this year, I'm with the conventional wisdom on that. I think that the moderation ends rather quickly in the next 2 or 3 years because of metals price inflation, which the economists bizarrely are not modeling at the macroeconomic level. It will also impact wind, solar, and battery and EV prices because they're made from those metals. That's the whole demand pressure is coming from those metals. Almost the entire increase that's been going on in the cost to build wind turbines, solar modules, and batteries is because of the increasing costs of the mineral inputs. It is true that the supply chain disruptions of the great lockdowns and some modest, comparatively, supply chain disruptions from the odious invasion into Ukraine haven't had an impact too, but they've been short term. This is a long-term phenomena. Roughly 70–80% of the cost of fabricating an electric battery today is in the purchase price of the materials. 80% of the cost to make a solar module is in the purchase price of the materials, not the energy costs, but the purchase costs of the materials. So if you, by the wind turbine, it's about 30%. So if you increase the cost of the materials by 200 to 300%, you should expect to see a curve like this. Again, this is IEA data. The vaunted continual decline in the cost of energy transition machines ended, and the prices are going up. That's been acknowledged in IEA and other areas. Now, but what they are now putting in play is the forecast that after 2 or 3 more years of rising prices for electric vehicles, batteries, wind turbines, and solar modules, these are rising real prices. Governments can hide that rise with subsidies for a while, but the real costs are going up. They're forecasting the curve will bend back down. The question that I would ask is a rhetorical one that I think answers itself when I pose it. On what basis, on what possible basis are forecasters saying that metal prices are going to go down after they've been rising in the face of these kind of demand pressures? I don't think they're going to go down, but this is a bet that people are making. This is the basket of principal metals that go into making an electric vehicle. Every Tesla, Hyundai, or BYD that's brought into Norway. The 20 to 25 barrels of oil equivalent of energy that's associated with making that vehicle, a lot of it is associated with extracting, finding, moving, and processing the metals and minerals. So when you look at the aluminum, steel, nickel, and cobalt, and look at the cost to purchase them to make a single EV, that cost per EV was around $4,000 before metal price inflation really started to kick in, and it doubled to about $8,000. A lot of that was a steel increase. The steel part, I think, may relax, but the aluminum, copper, nickel, those parts are not going to relax. You might have in your head, what does this picture look like for a conventional vehicle? One can have exactly the same graph. The input costs for the metals are less than half for a conventional vehicle, and they don't use, of course, any of the other suite of metals that are under incredible pressure. They use no lithium, no cobalt, essentially no neodymium. The entire motivation for this energy transition is anchored in carbon dioxide. It goes without saying. So I want to throw out one other fact to have in your head, and this is an important one, obviously, is that in the manufacturing of electric vehicles, in the acquisition of the materials and metals to make this, one necessarily consumes energy. The 25 or more barrels of oil equivalent of energy to manufacture an EV are almost entirely in the form of hydrocarbons globally, and that means it's carbon dioxide emissions elsewhere. Volkswagen, to their credit, published, this is one of the graphs from the Volkswagen study, published at their website, where they're showing total life cycle carbon dioxide emissions that are associated with driving an electric SUV versus a diesel-powered SUV. And what you see in their graph is the illustration, not in energy terms, but in carbon dioxide terms, that when the electric vehicle shows up in your driveway, it's already emitted about 14 tons of CO2. The conventional vehicle has already emitted about 5 tons to manufacture it. And then, of course, what you see is over the life of the vehicles that they both consume fuel and emit carbon dioxide, the battery one through the grid that it's using, and this is the average European grid, and of course the diesel one from the fuel. What you see in this study is that using this model, that is not until about 60,000 miles of driving that driving the electric Volkswagen in the European grid that you actually end up with a net reduction in CO2. And by the end of its life, you've got a net reduction of about 20%. 20% is not nothing. I just want to stipulate that's not zero. So the mythology that it's a zero emissions vehicle is just a pure myth. And eliminating all of the combustion turbines and all of the coal use on the grids of the world may happen one day. It's entirely possible to happen one day, but it's not going to happen in the time frames of the operations of these vehicles. So they're going to consume electricity in a fashion similar to this graph. That's simply what's happening in the world, not what's aspired to. The problem with this graph, by the way, is that the diesel line is fixed based on the physical chemistry of diesel and isn't changing. the electric line will change. This is a small battery. This battery in this model is half the size of the battery that 90% of Norwegians drive. This is the battery that's in a typical Tesla or a typical BYD is twice as big as this model, which put differently means if you put your finger on where the CO2 emissions are to deliver that electric vehicle to Norway, it's more like 25 tons. Now, in Norway, on a hydroelectric grid, that means that you do end up saving emissions over the life of the vehicle, but not that much. And what the big problem is that people will say, well, what we're going to do now is just change the chemistry. We'll use lithium iron phosphate. We'll use lithium manganese phosphate. We'll use different classes of chemistry. You can change the classes of chemistry. You can change the mineral soups, but it doesn't have a material difference at the high level of abstraction on the quantities of materials required. A typical electric vehicle battery, without regard to the chemistry it uses, weighs about half a ton, requires about 250 tons of materials to be mined somewhere on the planet to make that battery. It doesn't matter what class of chemicals you use. And the idea that we will fix this problem by having new magic batteries, batteries that are profoundly better than the batteries we're using today, is not a bad response. Technology does get better. Technology will get better, but it takes time. I think it's important to have in your head two simple facts. The lithium chemistry was discovered, invented, if you like, in the mid-1970s. You may all know this, by Exxon chemists, and was commercialized by Sony until almost 20 years later in the early 1990s. And of course, famously, it became possible as economies of scale and manufacturing expertise improved almost 20 years later with the emergence of the first Tesla S sedan, I think 2009, if I recall correctly. So this is a very long cycle from new chemistry to, at scale, new classes of industrial batteries. And the scale will be repeated. There will be better ones 20 years from now, 30 years from now. But what we build today are the kinds of batteries we know how to build today. The characteristics aren't like Iron Man's module in his back, in his chest, so he can fly. In comic books, you get energy velocities that look like computers. In the real world, the velocity of change in energy industrial systems takes decades, not years. The last couple of thoughts I'll leave you with in the mining world is what I think others may have called it this, but I facetiously call it the iron law of ore grades. Over all of history, the grade of ore that we mine has been declining, and especially for the higher value metals like copper, not iron ore as much, but copper and nickel and molybdenum and magnesium. And the ore grade, I mean, I assume you know what ore grade is. Ore grade is the percentage of the rock that you're mining that contains the thing you want. So copper ore grades are typically 1%. That arithmetically means that you have to dig up a ton of ore to get to 20 pounds of copper. And that doesn't count the tons of rock overburden that are in the way of the ore that you want to get to. So you dig up tons of material to get to pounds of metal. That has relevance. That has relevance in cost. That has relevance in environmental sense. It also has, to the point I made earlier, it has relevance to the carbon dioxide emissions and the energy consumed. It means that the world is chasing larger quantities of metals from declining ore grades, or put obviously and simplistically, as the larger quantities of metals are produced, larger quantities of energy will be consumed to produce those metals to deliver to markets. That increase in energy consumption as ore grades decline is nonlinear. It's another geological inconvenience in the physical chemistry of getting minerals out of ores. It turns out that this is a graph for the energy consumed per pound of copper as ore grades decline. So your x-axis is ore grades going down this way, and the y-axis is the energy consumed per pound of copper. You can see that it is beyond obvious this is an exponential, not a linear curve. Or put differently, you're on the exponential part, and we're at 1% ore grade. So if you can't see the bottom of the x-axis, 2%, the big bunching of little triangles of the mines of the world are all around the 1%. And as you go below 1%, the energy consumed starts to go up exponentially. This is a non-trivial problem. It means that the future electric car, the future solar module, the future wind turbines, carbon dioxide emissions and metal requirements are rising non-linearly just to fabricate them. So never mind whether they're available and what they cost, just to fabricate them will require the world to consume fuels and emit carbon dioxide at levels that are frankly unprecedented in mining history. We will solve those problems in due course, but in the mining industry, those problems get solved over decades, not in years. So let me end with one last very high level. We'll come back to the macro and the aspirational challenge that we have with an energy transition. In my mind, the energy transition is not one about replacing hydrocarbons, quite frankly. It's about supplementing them and minimizing their use. And it's a good thing. Setting aside whether or not carbon dioxide emissions should be minimized, and I'm not making a case whether that needs to be accelerated or decelerated. It can't be accelerated is the point that I'm trying to make, is that the reality is that we want to minimize it, so we do want to have more windmills, more solar arrays, more nuclear power, more, to use the line that was used by former President of the United States, we really do want all of the above. The transition that's required is to make the pursuit of all of the above more economically efficient, more environmentally tolerable, and more economically affordable. This is a much different challenge than the challenge that's being presented at the transition to a world without hydrocarbons. And it's going to be very difficult to achieve that because of this underlying reality, that this is over 1 century of data. Again, this is IEA data, of the year-on-year change in energy demand for the world. Now, what you can see is that the absolute percentage rate increase is declining, but it's declining over a larger base, so you all know what that means in investment terms. 10% on a big number is much more than 20% on a small number. So the percentage increases are declined, but they're on a much bigger base. The most important takeaway from this trend line in the world is below the axis. The periods of time and the frequency and the depth of declines in absolute demand for energy have evaporated. The world needs more energy every year, and there are very few periods in modern history for the last 50 to 70 years where there's been any absolute decrease in energy demand year on year. This means, put differently, that the world's appetite for energy and energy minerals and for energy materials is going to increase, not decrease, in the usefully foreseeable future. Efficiencies don't change this. We've been becoming more efficient for more than a century. In fact, we've been becoming more efficient for centuries. The efficiency metric increases demand because, in economic terms, efficiency reduces the costs of the thing that you're producing. And since the world needs more energy, this is absolute demand for energy, efficiency will actually accelerate this phenomenology. The last thing I'll leave you with is this thought, because my book, which I am obviously promoting by mentioning its fact, but it's not the subject of my remarks. My book called The Cloud Revolution is about energy's in the book, but about the broad technology trends that are underway in the world today. I'm convinced, and I try to prove in my book, that we are at a pivot in history. We aren't at an energy pivot in history. We are at a technological pivot in history, not unlike the one of the 1920s, where the magnitude, nature, and convergence of technology revolutions across the domains of information, material science, and machines promises economic boom, really unprecedented in history over the coming 50 years. I think it's really quite encouraging, quite remarkable, but it will require more energy and more diversified forms of energy. We'll have to produce it in ways that we find acceptable. Or put distilled in the most simple terms, if we're looking at how societies use energy as opposed to how societies produce energy, engineers invent energy demands. It's self-evident that there was no demand for energy for flying until the invention of the airplane. There was no demand for energy for cars until the invention of the car. There's no demand for energy to make computers work until the invention of the computer and the proliferation of computing. Global computing today uses more energy than global aviation. And the idea that we won't invent new reasons to consume energy in the future is not just naive, it's not true. So to give you just 2 examples, the cloud is a phenomenology different than the internet, subject for a whole other speech. But the net increase in demand to operate the infrastructure of the cloud is likely to increase a net increase in energy demand equal to what's already happened in computing, which is, to put it in oil terms, something on the order of 4 billion barrels of oil equivalent of net new energy demand to fuel Siri in the cloud, so to speak, not Siri as our host. And similarly for robots and drones. In fact, I'll leave you with this one last thought. The automation of the world through ChatGPT, which is virtual automation, through actual mobile robots that can help in mines, help in manufacturing plants, are already helping in warehouses. They all consume energy. Robots are the most complicated machines man has ever invented next to the car. It will take minerals and materials to make them. They will consume energy in their manufacturing and in their operation. Or to put it in very simplistic terms, robots eat too. They will be hungry and they will consume energy. We will supply it. It will cause economic growth to rise, and it will cause more, we'll call it chaos. And to finish on a note where I think Tim is right, this will be the domain of stock pickers, not momentum traders in the future, because this looks like a very complicated future for the energy supplies of the world. Thank you.
Now we're going to bring in an ESG specialist to challenge you. And he's been named a leading star under 30 by Dagens Næringsliv, the newspaper. And he's from the hometown of Erling Braut Haaland. Please welcome Sondre Myge.
All right, Mark.
A leading star under 30.
Well, yeah.
Am I a leading star over 30, I hope?
With that presentation, I would definitely say so. And thank you very much for it. It really turned out to be a reality check, I would say. I think one of the key takeaways I have from your presentation is how you talk about clean tech being a transition to solids from liquids and gas. And as you point out, there is a significant undersupply, both in terms of the absolute volume, the pace of that volume, and the ore quality of those materials. And so with that in mind, should investors prepare for a prolonged period of restricted supply in energy markets?
Yeah, I think we're in a period of underinvestment in all energy markets. So you all probably know this. Skagen team knows this. The world is underinvested in oil and gas for the last pretty close to decade. So even if you think we can achieve a peak in energy demand for oil and gas, the supplies have to be replaced, and investments are not commensurate. Same is true for minerals. So we're short on midterm investment, that is the 2 to 5 year time frame, in all energy markets, which translates into a pretty bullish price impacts on energy commodities I suspect for a very long time. Unfortunately, how long it lasts will be political. It will relate more to politics than it will relate to what engineers can accomplish.
Because another topic I see you write about often is the role between technology and society. You touched on it on your final slide. Curiously, we had EV trucks driving around Norway 100 years ago.
Yeah.
And given that the technology behind EVs is as old as the combustion engine, why did we not stick with the cleaner option to begin with?
Well, first because engineers knew that the batteries weren't cleaner, they were different from the very beginning. So people who build batteries I ran a lithium battery company for a while as an interim CEO. So I learned more than I really wanted to ever learn about the physical supply chain and the suppliers and the problems in the battery industry. Edison had a famous quote that some of you may have heard. It's not apocryphal. It was largely true. He just said there are liars and then there are battery salesmen. And so it's a version of the Mark Twain line about statistics. They're not cleaner. They're different. You're making trade-offs, which is true in all the engineering world. It's true in all the energy world. And the trade-offs are not irrelevant, but they are trade-offs. So the nomenclature is misleading. The reason the internal combustion engine won is because it's better, not because it's better everywhere and all the time. I think that we'll probably see a world where something on the order, and I'll pick a number based on my research, but let's just say 20 or 30% of all light-duty vehicles will be electric at some point, roughly speaking, which would be quite remarkable. It would be a massive growth from where we are of on the road, 1% of all light-duty vehicles are electric. So that would be a massive growth. But it would impact global oil demand by about 2 percentage points. So what you have is a world where both are possible technologically. A lot of combustion engines for a lot of things and a lot of electric motors for a lot of other things. So I'm in that camp. Again, I'm having trouble with this transition idea because the underlying energy economics and the physical realities don't support eliminating one, but rather amplifying, modifying, and moderating one.
I was surprised when we had our first conversation and how adamant you were that there is no such thing as an energy transition. So I do have to try to challenge you a bit on it. I read an interesting factoid the other day which said that Western countries needed 1 kilo of carbon dioxide to produce 1 unit of dollar GDP.
Right.
China will use half, and industrializing countries will do the same with a third of the CO2 input.
Right.
So how does this decoupling of emissions from economic value creation fit with your belief that the idea of an energy transition is diluted?
Well, again, it's nomenclature matters. So what technology does is it creates economic value. So you can accelerate economic value more than you accelerate the quantity of consumption of materials and energy. We've been doing that for hundreds of years. So you get more dollars for less input of either materials or energy. That's been going on for a long time. It will continue. But that's not a physical decoupling. So that's why I used the OECD graph of the physical quantities of materials. We went from 25 gigatons of materials consumed globally to 100 gigatons of all materials. But the GDP of the world, so that's a 4-fold increase in physical stuff. The GDP of the world over that time went up more than 12-fold. So you have a decoupling in that sense. But people think that means using less. It's less per dollar. It's beyond obvious a different thing.
One final question? Yeah, I think we can do one final quick one. You're, after all, the host of the Last Optimist podcast. And so in that spirit, what gives you the greatest optimism for the future of humanity?
Well, it's hard to be an optimist these days, I have to confess. That's why I'm the last one. Yeah. First, we're humans, we're very good at technology. Human beings are wired to do technology. It's what we've been inventing, ways around keeping nature from killing us and ways to make life easier for all of human history. And I do think we're at a pivot point of accelerating our capacities in that. So I'm optimistic about that. And that will mean, by the way, that I do think, and it's, again, a subject for another day, we will compress the time needed to open new minds. We will find ways to, we already know technologically, we can find minerals faster, we can mine faster, we can take dangerous labor out of mining, for example. So I know all these things are possible that weren't possible just 20 years ago. So I'm very optimistic that we'll achieve many of the goals we want. I'm just maybe slightly less optimistic that we'll develop the political patience for how long it will actually take, let's just say.
Excellent.